In order to help you work through these problems again, I'm going to give you a couple clues, some of the most important points for each of these syntheses. In this one, we can see that we have an ether, and we know a number of ways of preparing ethers. Probably the most common is the Williamson ether synthesis, right? So if I take an alkoxide and add that to some alkyl halide, right, I can do SN2 substitution reactions to give me ethers as products. And one of the requirements of the Williamson ether synthesis is that the carbon with the leaving group, in this case this one, it must be primary. If that carbon is not primary, then the alkoxide will more likely do E2 elimination to give alkenes. Another way to synthesize ethers is through the condensation of alcohols. So if I start with two different alcohols, we'll call that R1 and another one R2. As long as those alcohols are capable of doing SN1 or SN2 reactions at the carbon attached to oxygen, then when I treat these with oxyacids, like sulfuric acid or phosphoric acid, then I'll do a condensation reaction to give me the ether. It's condensation because one of the byproducts is water. Alright, so for this problem, when I look at it, there are two things that I notice right away. One, that it is an ether, right? And two, that it's a cyclic ether. If I look at the starting material, right, it's also a cyclic compound, but I've got a 5-membered ring here versus a 6-membered ring. And the temptation is to say, all right, I need to look up or find a reaction that can insert an oxygen atom in between two carbons, and then I'm done. And if we knew chemistry like that, that would be awesome, right? We'd be done. Our synthesis would be one step. But unfortunately, we don't know any reactions that can just insert an oxygen in between these two carbons. So I'm thinking strategically that I'm probably going to have to somehow open this 5-membered ring and then reform a 6-membered ring with an oxygen atom inside. So what do I mean by open this 5-membered ring? That means I'm going to have to break a carbon-carbon bond. And right away, there's only one reaction that we've learned that can break carbon-carbon bonds, and that's ozonolysis. Right? So if I want to break this bond, right, I'm thinking ozonolysis with ozone. All right, that gives me a little clue there, and we know that ozonolysis gives me ketones and aldehydes as products. Well, my clue here that that's the correct strategy is I could form this ether through the condensation of a diol. Right? In other words, I could make this bond right here, this oxygen-carbon bond, through a diol that looks like this. If I protonate the secondary alcohol, right, that can leave to give a secondary carbocation, and then the primary alcohol oxygen can add to it. Right? You could probably draw SN1 or SN2 reactions, depending on which carbon is the leaving group. Right? But I'm thinking about a process that looks like that. All right, that's good news because that's a diol. Right? And that diol then, right, I'm thinking I can get that from ketones and aldehydes. Right? So when I think backwards another step, I'm thinking what molecule, right, will have both of those alcohol groups as a ketone or aldehyde. Ketone and aldehyde. Right, so that's your clue. Right, what would that look like? And then can you get that through ozonolysis somehow? All right, in this question, we again are tasked with preparing an ether. And before I outline the strategy, let me see if I can find the carbons that are in common to both of these. So if I just highlight these in blue, it looks like these carbons are in common to both the starting material and the target molecule. And that gives me a nice clue that I need to form this carbon-carbon bond somewhere in my synthesis. So I'm running through my head, what are all the carbon-carbon bond forming reactions that I know? I know I can do alkylation of alkynes. That's one possibility. I can do Grignard reactions. I can make carbon-carbon double bonds, right, through Wittig reactions. Right, and there are many more, some of which we're going to learn later in the course. Right, so then when you get to that step, you have to look these reactions up and see if any of them seem reasonable. Okay, now the other thing that I see is I do have an epoxide as my starting material, and that epoxide is not in the target molecule. So I'm most likely going to do a ring opening of that epoxide. Some nucleophile is going to add to either the least substituted carbon or the most, and I'm going to break a carbon-oxygen bond. So this oxygen atom here, right, is probably this one in the product. So if I'm thinking ring opening of an epoxide, perhaps I can form a Grignard reagent out of the benzene and add that to the appropriate epoxide. All right, so I'm thinking, get this piece here, right, as a Grignard, and form that carbon-carbon bond by adding that to an appropriate epoxide. All right, that should give you a good start. All right, in this question, again, I'm forming another ether, and I'm going to find the carbons in common. Right? That's usually where I start. What is the same? That kind of gives me a clue on what smaller pieces that I need. So I'm going to highlight the carbons that seem to be in common, and that's basically the six-membered ring. Right? All of those carbons in the target molecule are also found in my starting material. And what I can see is there's an extra carbon in the starting material. Right? So this is one of those odd syntheses in which I need to remove a carbon atom somehow. In other words, I need to break this carbon-carbon bond here. Okay, that strategy is the same as the previous question, right? The only carbon-carbon bond breaking reaction I know is ozonolysis. And I know that I have to do ozonolysis on alkenes. All right, so the reactions I'm thinking of are ozonolysis, wow, can't spell today. Of alkenes, right? And you should be able to figure out how to turn that alcohol into an alkene. Now we know that ozonolysis gives me ketones and aldehydes as products. So I need to somehow make this ether eventually from a ketone or aldehyde. Well, I know that I can get ethers from alcohols, right? I can do Williamson ether syntheses. So perhaps I can eventually get an alcohol that looks like this. And then the question is, can I get that alcohol from a ketone? Right? And what would that ketone look like? I think the answer is yes. You determine what the ketone looks like, and then how you would make that. Here there are lots of clues. The target molecule has a trans alkene, and the starting material is an alkyne. Right, so this synthesis is very clearly set up to do carbon-carbon bond forming reactions through SN2 substitutions of acetylides. So it seems reasonable then that I can get this trans alkene from an alkyne. Right, so that's what I'm thinking first. I'm working backwards from the target, okay, and I'm pretty sure I can get this from an alkyne. You have to determine what that alkyne would look like. Well, it's going to look very much like the target molecule. The only difference is, right, instead of having a carbon-carbon double bond, I'm going to have a carbon-carbon triple bond. I know I can reduce alkynes to transalkenes with sodium and ammonia, right, a dissolving metal reduction. And I can reduce alkynes to cis-alkenes with Lindlar catalyst. All right, once you've determined what that alkyne looks like, then the question is, how do you make this carbon-carbon bond here? Right? This is the carbon-carbon bond you eventually have to make, because if I count carbons in the starting material, I've got 1, 2, 3, 4, 5, 6, and I do the same thing in the product, right? Here's carbon 6, and then 7, 8. So I need to form a bond between carbon 6 and carbon 7, and I'll just remind you that acetylides, the conjugate bases of alkynes, very readily do SN2 substitution reactions with other primary carbons that have a good leaving group, right, like alkyl bromides. Okay, SN2 here would give me the internal alkyne. All right, so that should be a good clue. Those should be good hints to get you started. All right, the final functional group in this synthesis question is an acetal. Right, so knowing the functional group names of the things that you're trying to make is very important, because once you know the name, then you can get into your notes or go to the index in the textbook and start researching how to form those functional groups. All right, so I know that I can make acetals from ketones and aldehydes and alcohols. And if I'm forming a cyclic acetal, right, then the two alcohols came from the two oxygens that are in that chain, right? In other words, somewhere in the process, I formed these oxygen-carbon bonds. So in working backwards, right, the carbon that I've highlighted in red comes from the ketone or aldehyde, right, and the oxygens come from, in this case, a diol, a chain with two alcohol groups in it. So you have to determine, what does that diol look like? Right, and another hint here, if I look at the starting material and count carbons, right, I've got 1, 2, 3, 4, and in the product, right, at each carbon with an oxygen, I have 1, 2, 3, 4, and here 1, 2, 3, 4. So it seems to me, because that molecule is symmetrical, right, that I can get all 8 carbons from 2 of the starting material. Right, it's going to take a couple steps, and then somehow join them together. Right, again, I'm thinking I have to form a bond between the carbons 1 and 1 prime here, somewhere in my synthesis. Okay, and what are my carbon bond forming reactions again? Right, I have to run through them, right, and then see which makes sense. Right, so again, I can form carbon-carbon bonds through Grignard additions. Right, I can form carbon-carbon double bonds through the Wittig reaction. Right, and as we've seen before, through alkyne alkylation. Right, but that doesn't seem like that's going to work in this case. All right, there you go. The target molecule here is an ene-amine. And I know I can make ene-amines from their respective aldehydes and amines. Right, the bond that I have to form in an ene-amine is the one between the nitrogen and the carbon here. So you have to work backwards then and decide what does the aldehyde look like in this case? Right, you're going to disconnect these two pieces. And what does the amine look like? And once you've done that, then your synthesis becomes much easier. Right? I'm sure you can devise a way to create this aldehyde eventually from ethylbenzene. This one is a little bit tricky because the target molecule is an alcohol. And what makes it tricky is you know tons of ways of making alcohols. Right? And so sometimes it can be a little daunting to run through all of those methods, right, to see which one works. The other tricky thing about this synthesis is you can start with whatever you want, right? So this one is really open-ended. The only requirement is that you have to start with either alcohols and or alkyl halides that have equal to or fewer than 6 carbons, right? So that's the only requirement here. All right, so I want to show you a pattern, right, that can really give you a good clue on how to do that synthesis. So what I notice here is that I don't just have an alcohol, but I have an alcohol group that is adjacent and trans to some other group, in this case an ethyl group. And whenever I see that pattern, it doesn't always work, but the first thing that I think of is ring opening of epoxides, right? Because I can create new carbon-carbon bonds, this one, and break, oops, let me do that a little better, and break carbon-oxygen bonds in epoxides to give me alcohols. So that's what I think, that's what I want you to think about here, right? Could you do some type of carbon nucleophile addition to an epoxide and do an anionic ring opening? All right, this one is a classic one. All right, again, let's start with the functional groups. Okay, it looks like I have to start with a ketone. Clearly the product or the target molecule has more carbon atoms than the starting material. So I'm going to form carbon-carbon bonds, right, to give me an alkene. Right, so you have to search through your list of flashcards and find out how do you go from ketones to alkenes, right, and forming carbon-carbon bonds in the process. Now, what bond do I have to form? Well, that's pretty easy to spot. Right? Again, I'm looking for things in common, right, and it looks like the carbons from this 6-membered ring are right here that I've highlighted in blue. Okay, and so it means then, and then the benzene ring, right, would compose the remaining carbons. So that's my clue that I have to form a bond between those two carbons, right, and make an alkene. So in my retrosynthesis, I'm going to do a disconnection. Right, I'm thinking backwards, and I'm wondering what type of reaction forms double bonds between carbons. Okay, and the clear answer here is the Wittig reaction. Right, so a Wittig reaction connects carbon fragments together and forms alkenes. And we do Wittigs between, in this case, a ketone right, and then I'm going to need a Wittig reagent, right, a phosphonium salt that I'm going to treat with a strong base to give me the Wittig nucleophile. Right, so you got to think about what does the ketone look like, what does the phosphonium salt look like, right, and then if necessary, how do you make those from the starting material? This one at first glance seems like it's pretty easy, right? I just got to change the bromine group to a hydroxyl group, and then change the hydroxyl group in the starting material to a thioether in the target molecule. Okay, but if you try to treat those separately, right, if you try to do it stepwise, you'll run into trouble right away, right? You'll get to a situation where you're hoping one group reacts and not another. So again, I want to highlight a pattern that I talked about in a previous example, right? I have an alcohol, and it is adjacent to another group that could potentially be a nucleophile, right? If I had a sulfur atom with 3 lone pairs and a negative charge, that'd be an anionic nucleophile. And so whenever I see that pattern, right, I'm always thinking ring opening of epoxides. Okay, so I'm wondering, is there something that I could add, some anionic nucleophile that I could add to an epoxide to get me to this final target molecule, right? And another good clue that this is epoxide chemistry is I know that I can make epoxides directly from my starting material, right? If you know the name of this functional group, this is a vicinal halo hydrin. And I know vicinal halohydrins, if I treat them with strong base, give me epoxides directly. All right, this one's pretty straightforward, right? It uses the chemistry we've seen in some previous examples. Again, this is a cyclic acetal. So I have to review my notes maybe if necessary and look up how to form acetals, right? And when I do that, right, I'll remind myself that the anomeric carbon, the one where both oxygens are attached, comes from a ketone or aldehyde. In this case, that one's got to come from an aldehyde because there's a hydrogen here. And the 2 oxygen atoms come from alcohols. And because these oxygens are connected to each other, right, I'm going to get them from a diol. So now I got to work backwards, right, and determine what does the aldehyde look like, and then what does the diol look like. And that's the hardest part of this step. So I've got an aldehyde and a diol. And then, of course, how do you make those, right? How do you make the aldehyde from the starting material? Just a quick clue here. This is an imine. So I need to review my imine chemistry. And I know that I can make imines from ketones and aldehydes and amines. Right, so in this case, it's got to be an aldehyde and some amine. So you have to determine what those are, right? But I'll remind you that the bond that you're forming is this one, the carbon-nitrogen double bond. And the nitrogen comes from the amine, the carbon comes from the ketone or aldehyde. Again, this question is pretty open-ended, right? Your eventual starting materials can be anything as long as they have 5 or fewer carbons. All right, this problem is challenging unless you know one key reaction, right? So I do have an alcohol as a functional group, but what I see here that's most striking is a cyclohexene ring. Whoops. Right, so this is cyclohexene. And if I look at my required starting materials, they have to have 4 or fewer carbons. So somehow I have to build that cyclohexene ring. And there's one reaction that I know that makes cyclohexenes directly, and that's Diels-Alder chemistry. So there's your big clue, right? I'll let you figure out the rest. We're going to have to use a Diels-Alder reaction somewhere in my synthesis.